This is a circuit that I designed which makes waveforms that look like action potentials from neurons. And unlike my video I posted last week, which uses entirely analog circuitry to generate waveforms which look like this uses a combination of analog and digital circuitry. The digital circuitry being a microcontroller. This is a programmable 8-bit microcontroller, an ATtiny 85, and I write software on here to determine when to fire action potentials. And there are two main inputs. The first one is an analog voltage somewhere between 0 volts and the positive voltage rail, which here is 5 volts. By adjusting this potentiometer, I can change that voltage, which is sensed by the analog to digital converter on this microchip, and when the voltage changes, the action potential frequency changes. So now I have control over action potential frequency. But this was also done with the analog circuit. There's nothing new here. One of the cool things that we can do, since we have a microcontroller, is we can use a pseudo-random number generator entirely in software to change the spacing between action potentials. So by removing this jumper here, we can switch to random mode. Now the action potentials are fired randomly, and action potentials with random timing is a little bit more physiological. It's more natural. Neurons in the brain fire more like this than an entirely regular spiking pattern. There's one more cool thing about this circuit, and to understand it we've got to zoom in on the action potentials a little bit closer. So I'm going to increase the action potential frequency and zoom in horizontally. Alright, this is what a single action potential looks like. There is a resting voltage, and then there is a depolarizing phase, because normally in the body this would be about negative 70 millivolts, and as we approach 0 that would be considered depolarizing, and then this fast depolarization would be followed by a fast repolarization. And due to the circuitry in the cell, sometimes it overshoots the original rest voltage by several millivolts. This overshoot is called an afterhyperpolarization, or an AHP, and different neurons have different shapes of AHP. In this circuit I can adjust the AHP by twisting this knob here. By rotating it counterclockwise, I can produce a larger AHP or a smaller AHP. So I can customize the shape of this neuron. So let's take a look on the larger view what that looks like. I'm going to slow down the action potentials again. And if we saw a cell like this with very small AHP, this would be typical of many cortical excitatory neurons, just as an example. And if I twist this counterclockwise, we start to generate action potentials with larger AHPs. Cells with larger AHPs like this typically are inhibitory interneurons, just to make a broad generalization. And we can still change the frequency like before. So in this circuit, we use the microchip to generate either randomly timed or regularly spaced action potentials. We can adjust its frequency, and we can adjust the after hyperpolarization. So this is a pretty cool design. Let's take a look at how it works. This is the circuit that generates these action potentials from a single microcontroller pin. And the way this works is we adjust the current on the pin. We can either supply current, sink current, or just kind of float and do nothing. That floating state is called a high Z state or a high impedance state. And most of the time this pin is in that high impedance state. So the way that we generate an action potential is by charging or discharging this capacitor here. When this pin is in a high Z state, this capacitor isn't being charged or discharged, it's just resting. When we go from the Z state to the high state, we start charging this capacitor. Then we go down to 0 volts and we start discharging this capacitor as current flows in the opposite direction. And then we go back to the high Z state, and then this capacitor slowly returns to its original voltage. All of that is series decoupled through this series capacitor. And then we have an amplifier here. This is an LM358. It's an operational amplifier chip that has 2 amplifiers in one chip. This one is used to amplify this small action potential like waveform, and it also uses this capacitor up here to provide some low pass filtering. So if we were just to look at the voltage on this capacitor, when we charge or discharge a relatively large capacitor through a relatively high value resistor, we don't really cause an RC type curve, we cause more of a linear, like a triangle shaped curve. So if we were to probe this point here, we'd see something that looks very triangular. By low pass filtering the triangle wave, we produce something which looks a little bit more natural. It's a little bit smoother, like an action potential. And then here, by adjusting the resistance to the voltage rails, we can determine how much overshoot there is. And that's kind of hard to understand beyond the fact that it's just a property of what happens when we discharge this capacitor. We then take the voltage here and amplify it by 1. So we run it through an amplifier with a 1x gain. So we're not actually amplifying it. The purpose of a unity gain amplifier is to serve as a buffer. So if we were to load down the voltage out here, it wouldn't really affect the circuitry here very much. So we can be very rough on these outputs, and we're not going to change these small artifacts which contribute to make the AHP. So let's take a closer look, I guess, at the output of the microcontroller pin. I'm going to hook a second probe here so we can see what that voltage looks like. Alright, I'll turn on channel 2 and we'll zoom in horizontally. And this bottom trace is the voltage on that microcontroller pin. Normally in that high Z state it rests somewhere in the middle. That's where it's being pulled currently. And then when it goes high, we start charging our capacitor, so this rises up. When it goes low, we start discharging our capacitor, so it goes down. And that's pretty much that simple. So all in all, we have a circuit which uses a microcontroller to generate timed pulses, uses an amplifier and low-pass filter to shape them into something that looks like an action potential. We utilize a feature of series capacitance and adjust the current flow to the voltage rails to create an artifact which looks like an AHP. And we can capture the output either at this point here, which will be an action potential centered at 2.5 volts, which is about halfway between 5 volts and ground, or we can run it through one last series capacitor to grab an action potential like waveform which is centered at 0 volts. And finally, I can't say it enough, the most useful part of the circuit is the fact that by removing this jumper here, we can allow the pseudo-random number generator in the microchip to generate random appearing action potential waveforms. The circuit design for this circuit, as well as the code which runs on the microchip, is available on my website, SWHarden.com, and the link is in the description.